I have a question. How do I share my screen on this?
Uh, there should be a present now option that looks like. Oh, which device are you in?
I'm on this other one. I have two devices.
No, which like what type of device are you using?
It's an HP Spectra.
Is it a
It's a
laptop?
laptop. It's a laptop.
Right. So there should be a present now option below.
Yeah. So the
Like,
share button is gray.
is it now? Is it there now? I think that was my bad. Can you
No,
see it
it's.
now?
I mean, it shows the. Okay, I got it. Got it.
Okay, yeah. Okay, that was my mistake. I'm sorry.
Can everybody see my screen?
Yep.
Um. Okay. So hi everybody. I'm Ishank, and I'm going to be talking about projective maps today. And so just by you, I want everybody to be talking in the chat box. So be vocal. I don't want this to be a one person talking the whole time. So just by telling me, how many of you know what projective maps are? Someone doesn't know it. It's okay. Anybody? Okay. Okay, got it. Does anybody know what a projection is? Anybody heard what a projection is? Okay,
Any
Aditya,
path?
yeah, Aditya, tell me what a projection is. Okay, so like a shadow. Okay, that's right. Anybody know what a projector is? If you've seen what's a projector? If you've gone to the movies or seen something, you guys can hear me, right? That projects something. Simple. Yeah. Okay. The source of light. Exactly. That blue thing that where everybody stands in front and you see shadows. Okay. Does anybody know what a cross ratio is?
What?
A cross ratio. Can you hear me? Am I audible?
Yeah.
Okay. No worries. We're gonna go over all of this. Does anybody know what a conic is?
They are figures that are obtained from the by cutting a plane and with the cone, like when a
Yep.
plane intersects a cone. So the
Yep.
geometrical figures obtained.
Exactly. Got it. Okay, so we're gonna go over all of these, but we're gonna give slightly different definitions of a conic. We're gonna talk about projections. So projections, usually what you've heard of up till now, are 90 degrees, right? So you have a line, a projection on this line is something like this, right? That's pretty much what a projection is. Do people agree with me on that? I mean, that's your typical definition of projection. So we're gonna get rid of this projection. We're not gonna think of projection like this. We're also gonna get rid of the notion. Well, okay, conics are going to be cross sections of cones, but we're gonna give more terminologies for that, and we're gonna go over things from a different level. So basically, what I'm asking for you is to kind of get rid of your preconceptions before we go on, because okay, so. So first, I want to start off with a little bit of the of how projective geometry started. So projective geometry actually didn't start as math. It started as art. And so what does this look like?
It can be interpreted in different ways, I think.
So what's one interpretation?
Like it can be considered as a 2D as well as a 3D figure.
Assuming it's 3D, what does it look like?
It's like a plane cutting another plane.
Yeah. So I'm basically going for a chessboard. Does it look like a chessboard?
Yes.
Okay, got it. So usually chessboards have squares, right? This looks like a 4x4 chessboard, but there are no squares in this figure. Would you all agree with that? 2-point perspective, exactly. So I think Aditya knows about art. So yeah, 2-point perspective. That all started with projective geometry. So in fact, you can actually tweak these things and you can get different types of planes. right? And they all look like chessboards, but looking at them at a different angle. And that's basically what projective geometry is going to work on. Okay. Okay. So now we're gonna go into the axioms before we go. So does anybody know about the Euclidean 5 axioms? Okay, somebody name the first. What does the first axiom say? You know what? Okay, fine. Let's not go into the axioms. That'll be like CBSC. Okay, so basically what the axioms state is you can make a circle, you can make a line, you can make a point. Right angles are equal, and parallel lines exist. That's basically what the 5 axioms say. In projective geometry, we don't have angles at all. You'll see what I mean by that in just a bit. But we only have lines and we have points. And there's something called an incidence structure. So in projective geometry, you have a set of points. You have lines and you have an incidence structure. This incidence structure says basically when is a point on a line. So everything in projective geometry, what we're going to do is we're going to only think about points, lines, and which point lies on which line. Got it?
Yes.
Okay. So okay, so the first axiom of projective geometry says that each line has at least 3 points. This is kind of obvious. I mean, you don't need to be really smart to figure why this must be true. It's axiomatic. Okay. The second axiom states that for any 2 lines, they will always intersect. Wait, sorry. I got it back right. The second axiom states that between any 2 points, there is a line. Is anybody having problem understanding the first 2 axioms? Okay, good. Okay, so the third axiom states that whenever we have 4 points, A, B, C, and D, whenever A, B, and C, D intersect, if they intersect, then whenever A, D, and B, C intersect, then A, B, and C, D will also intersect. This is the third axiom. Does anybody have trouble understanding this axiom? Did somebody raise a hand? No? Okay. So everybody understood this axiom. Great. What is the consequence of this axiom? Like, why couldn't we just say that any 2 lines meet? Why did we have to put it this way? Does anybody know? I mean, we could just say that 2 lines meet. So Meenakshi, yes, they're parallel. If we take ABCD parallel, they meet at infinity. Got it. But I could just say that any 2 lines meet. I don't need to use this extra point. I could just say that take any 2 lines ABCD, they meet somewhere. EDZY, what are you talking about the in circle? I don't understand. Anybody have any ideas? Okay. So in projective geometry, we actually haven't defined a plane yet. And we'll actually be working in 3D for most of this video. And don't get scared, it's gonna be easy. But in this case, when we say ABCD intersect, that basically defines a plane without defining a plane. It's a clever technique. Got it? Did everybody understand that? Because what basically we could have is we could have 2 planes like this, and we have skew lines, then they don't meet. Okay. So that's how it's a very clever way of yeah, we can define a plane by 3 points, but we've only defined an incidence structure. I mean, the only way we can say something is by saying point P lines on point L. We have nothing else. So defining a plane by 3 points, how would you define that? Okay, so I think the three axioms are pretty clear. They are axiomatic. You don't need to prove them by definition. And so that's just three axioms. Okay, so now just using the incidence claim, right? What can we define? How can we define something with incidence? So the first thing we could say is, how do we define a triangle? What's a triangle? This is actually pretty easy. So anybody, a geometrical shape, three non-collinear, join three non-points. Exactly. Take any 3 points, they form a triangle. Okay. You could also just as well say take any three lines. They form a triangle with non-collinearity. Yes, non-incidence, non-collinearity. Exactly. So that's how you could define a triangle. But no, with just the fact that if 2 points align each other, we don't have any angles. There are no angles in projective geometry. Okay. So if we don't have angles, what does that mean we don't have? So basically we're just saying that a point lies on a line. We have no concept of an angle.
Hey, can I say something?
Yeah, of course.
Okay, you're saying that there's no angles, means there's no intersecting lines.
No, so there are angles, but there's no concept of an angle. Like you can't say that two angles are equal. You can't say that an angle A plus angle B is 180. You
Okay,
can't measure angles.
yeah.
I mean, of course there are there are angles like that, but there is no defined notion of it.
That is that there is no notion of equality or inequality in terms of angle, right?
Yes. And so for three lines, they aren't making correct. So like we said, okay, so here we said these 3 points shouldn't lie on a line. Here we're saying that three lines not going through a point. Okay. And I actually want to take just a second. So further going back to the triangle example, note how it's kind of dual, right? We can say 3 points just as well as we can say three lines. We can say 3 points lying not on a line, or we can say three lines not going through a point. Okay, that's just duality, which we will get to. Point line duality, exactly. So we may get to that if we have time. So by no angles, what that means is we're basically throwing out of the window isosceles triangles. Okay, an isosceles triangle does not exist in projective geometry. We're throwing out squares, all of that. We're throwing out circles are defined by that. We're throwing that out. There's no concept of a circle defined in this way. We will define a circle later. Okay, so any questions to here?
No.
Okay. So now I want to go back to the fact that two lines meet. So for those of you know, projective geometry states that parallel lines always meet. And what we basically do in projective geometry. So those were the axioms. Like, why would we have to determine a circle if it's a curve? Well, circles have lots of really good properties that most curves don't do. Like, for example, circles have the fact that this angle is this angle. Circles have fact like Pascal's theorems are valid for circles. These things are not valid for any curve. So by a circle, we're talking about we need a structure that gives us those properties. So we will define a circle, but not using this. Okay. So back to how we develop the plane synthetically and not axiomatically. By that, what we basically do is for any two parallel lines, we intersect them at infinity. Okay. And for every single parallel line, we give them an infinity. So each direction vector has a corresponding infinity to it. Does that make sense? So if I go back to this example, if you look at it as a plane, right? If you look at it as a 3D if you look at it as a 3D structure, then you can see that all these lines A, B, C, D, these lines, the corresponding infinity point would be F, because that's where they meet at infinity. Okay. If I take the diagonal points, if we're still thinking of them as squares, if we take BD, AH, TQ, all of these points, they will intersect at G, because that's the infinity point corresponding to these diagonals, because they're all parallel. If we thought of it as a plane, does that make sense? Okay, got it. Okay. So now we're going to go on to what a projection is. So we're actually going to call it a perspectivity for historical reasons. That's what it's called. So what we basically do, so now we're going into a projective. This is our first projective map that you're going to learn. What it basically does is it takes a point A and it sends it to A dash. Takes a point B and sends it to B dash. Sends C to C dash, etc. Does anybody have any problem with how I'm defining a perspectivity? Okay, got it. And so a combination of these is known as a projectivity. Okay, any problems still here? Any questions? A combination, okay, a composition. Okay, so I'll go over a combination. So it's basically like you had these points A, B, C. You first map them to A dash, B dash, C dash under this first O, and then you mapped it to a different line. And then say you mapped it to a different line under a different point, O2, and then you mapped it to A2, B2, C2. Then the map A to A2, B to B2, etc. This would be a combination of two perspectivities. Does that make sense? So like it would be composition of different maps. Okay, so that's what a projectivity is. Got it. So now moving on. Before we go on, I want to just have like a little problem. So my first problem for tonight is prove that there is a projectivity that takes any 3 points ABC on one line to any 3 points on another line. Okay, prove there is a projectivity. That's my first problem for tonight. Does everybody understand the problem? Okay. Does anybody want to try? If we can show there is a non-coincident line in space or plane, then we can show there is a projectivity. I don't understand. So I'll give a hint. Try going one by one. Like find a perspectivity that maps A to A dash first, regardless of where B and C go. And then try to keep A at A dash and try then to map B and C. Okay, so I guess I'll just go through it then. So O as the intersection of A dash, and B dash. Okay. So if you take this, then C would go to C dash, right? Okay, so basically, I'll go with it. If we have any 3 points like this, if we want to map B to B dash, C to C dash, and keep A as the intersection point, we can do that simply by taking intersection of B dash and C dash, because this point will remain fixed. Does everybody get this? Okay. Exactly. So what we'll do is we'll construct a. So A will remain fixed. So okay. So I'll just rigorously define what a perspectivity is really quickly. A perspectivity centered at O takes a point X to OX intersection line L2. That's a rigorous definition of perspectivity. So basically with this in place, what we do is we create an auxiliary line AC dash. Okay. And then we map B to some point B1 through this first projectivity. So this will map, so the projectivity at O1 would send A to A, B to B1, and C to C dash. And then after that, what we do, O always exists. Why would O not exist? Because remember, parallel lines always meet in projective geometry. In fact, if we want to axiomatically prove this, every line consists of these 3 points, so we can always find an extra point B on AC dash, and then any 2 lines intersect at O. Got it? I mean, if they were parallel, then O1 would be the point at infinity, which we can still use. Does that make sense? If it were actually, like, if it were the point at infinity, all these lines would be parallel. So B dash would then be parallel to this. Okay. And so any other point that we want to take would be then again a parallel. It would be parallel. This is actually, by the way, called a line perspectivity. Taking lines parallel to each other, this is called a line perspectivity. You also going to take like ABC intersection. How do I intersect? Okay, so you're saying intersection from here. Take perspectivity through this point X. Is that what you're saying? So, I mean, okay, so you want to take XA intersection L2. Yeah, how would you take an intersection of this line with this line? That all of the points would map to X. In fact, this wouldn't even be a map because it wouldn't be bijective. Does that make sense? Yeah. In fact, I should add here, O is not in L1 and L2. Otherwise, you don't get a map. Remember, all maps must be bijective. For every point, there must be an image, and for every image, there must be a pre-image. Otherwise, the map won't be well defined. Okay. So yeah, so we got ABC to AB1, C1, and now what we do is we map. And so now we can take this and just a map from here. Can there be cases where O exists between line? Yeah, of course. This is just the way I configured it. In fact, B dash could lie outside of A dash C dash. That's also possible. There could be many configurations. Okay, got it? Okay. So now I want to go on to another definition of a projectivity. But before we go, I'm going to introduce the cross ratio. So what is a cross ratio? Given 4 points, A, B, C, D, the cross ratio of A, B, C, D is defined as AC by BC multiplied by BD upon AD. And it turns out that this is such a useful property because when you take perspectivities, this thing remains constant. So whenever you take a perspectivity, this remains constant. Okay. Does anybody have any questions? Can anybody prove this? Okay, so I'll just sketch out a proof for the interest of time because I want to get into 3D projective maps. But basically what you show is that, yeah, you could use trigonometry, but there's actually well, it is a trigonometric proof, but it's actually quite beautiful. So you show that if you made this θ1, θ2, you can show that this is equal to sine of AOC by sine of BOC times sine of BOD upon sine of AOD. And the way you show this is by just considering the areas of each triangle. So the heights are the same. The ratio of the areas would be proportional to the ratio of the bases. And then you use the fact that the area of a triangle is half AB sine theta. And then all the OA, OB, OC, OD, they will just cancel out.
Hey, in this topic, you're saying that mapping the points. So can I use mapping as a joining?
Sorry, I don't understand.
Okay, you are saying that when I map this, so I can understand as a join the points.
Yeah, exactly. So we map A to A dash as in OA intersection that line. That is a perspectivity.
Okay.
Does that make sense?
Yeah.
Okay. So once we get this invariant, now this thing is the same for A dash, B dash, C dash, and D dash. So then this becomes A dash, B dash, C dash, D dash. Okay. So another perspective map that I'll just briefly go into is that if you have points A, B, C, D, take any point P, let those intersections be A dash, B dash, C dash, D dash, whatever. Take another point Q and let those new sections be A2, B2, C2, and D2, then this is a projective map. Wait, actually, I got a little ahead of myself. I'm so sorry. I'm going to actually backtrack for a second. Okay, so now we have shown that projectivities preserve cross ratio. Right? Everybody understood this, right? Projectivities preserve cross ratio.
Yes.
Yeah, okay. But actually, is the converse true? Is it true that if you map a line to another line, such that whenever you take any 4 points A, B, C, D, and their images FA, FB, FC, FD, then is it true that there exists a projectivity? If it's true that the cross ratio is always the same. If it's true that ABCD is equal to FAFB, FCFD. So given this true, does there exist a projectivity? So would that be true? What would your guesses be? So I'm saying that we're given a map. We're given a function f that takes any point x to some point x, f of x. We're given this map f. And this map has this property that whenever you take any 4 points, A, B, C, D, and they map to F, A, F, B, F, C, F, D, if you're given this, then can you represent that map as a combination of perspectivities? Is the question clear?
Couldn't we just map 3 of them like we did earlier, and then the 4th one is fixed? Is forced?
Exactly. So if we map, so there is a projectivity that maps A to FA, B to FB, C to FC. And the cool thing about the cross ratio is that I actually forgot to tell you guys this, but this is signed. So BD and AD are, the ratio is positive if they're in the same direction. Okay, so this thing, if you have 2 points D1, D2 such that AB, C, D1 is AB, C, D2, then this necessarily implies that D1 is D2. And you can do this with simple algebra because the fact that both of the terms are linear. Does everybody understand this? Yeah, okay. And so therefore, if you map any 3 points ABC using that perspectivity that we did earlier, using this perspectivity, this one, if you do that, then that perspectivity must necessarily send D to FT because of the fact that the cross ratio is the same. Does everybody understand? Okay, actually this thing is kind of special, and so they call this the fundamental theorem of projective geometry. Okay. Yeah, because there's one root. So fundamental geometry. So fundamental theorems aren't necessarily hard to prove. They just embody the spirit of that discipline. So that's why it's called fundamental. Like number theory, fundamental states that any number can be written as a combination of primes, and so on. Okay, so now we've got that. We can always find that any projective map is uniquely defined by 3 points. Okay. So right now I kind of want to just take a brief look backwards. So using the maps that we've done, perspectivities, you can do a lot of questions. You can chase them all across the figure, right? There are problems in which you can say that if you have like a symmedian, right? You can take that, you can take a perspectivity, you can send points to different points and then just ensure cross ratio is same, and then use those values to show facts in geometry figures. And that's it's basically called chasing harmonics. And it works really well. We're actually not going to go down that. Does everybody know? Does anybody know about this? What I'm talking about? Chasing harmonics. No. Okay, so for those of you who do know about chasing harmonics, we're not going to go down that path. We're going to work on purely projective problems. So I'm sorry, but we're going to move on. If you don't know, then you don't know. Okay. So now we're going to take everything what we did in. So right now we were all in two-dimensional, right? We mapped lines to lines staying in the plane. Now we're going to go to 3D. And so in 3D, what a perspectivity is you take one plane, you take another plane, and you define the image of the map by say gamma 1 and gamma 2, then okay, that's the natural analog for 3 dimensions. Does everybody understand how I've defined a perspectivity in 3 dimensions? Okay. So okay, so one thing that's so what would be some invariants in this? Where would lines map to? What would a line map to? If I take a line, what would be the image of a line? So the image of a line would be a line, because so we're basically taking all points on this line and seeing what that image would be. It would be a line because if we consider the plane, that this line and this point O makes, the image of that line would be an intersection of that plane with this other plane. And so then that would be another line. So lines map to lines. Okay. Obviously points map to points. And finally, incidence is preserved. That is, if a point P lines on a line L, then the image of that point lies on the image of a line. So we're only taking images of these points on this plane. So we're only defining this for the points that are on this plane. Yes, O does not, again, as before, O does not lie on gamma 1 or gamma 2. Any questions? Okay, so this is basically like the fun part. So basically, now you kind of might be getting out how art shaped this. You didn't understand. You have any question? Achha, okay, no doubts. So, so this is basically what projective geometry started as, looking at a plane from a different plane, like the projection that way. And so in projective geometry, what we're going to do is we're going to state that if a statement is true in this plane, then it must also be true in this plane. Okay. And we'll see how that works in just a bit. First of all, I want to ask, will cross ratio be preserved? Will cross ratio be preserved? Does anybody want to sketch a proof for this?
Couldn't you just consider the plane made by the point on the line and then do that?
Exactly. So you basically use the previous results on this plane, right? Is that what you're saying?
Yeah.
Yeah, exactly. Everybody got it? Okay. So yeah, so cross ratio is preserved. Incidence is also preserved. Now, so it's true that lines are mapped to lines, points are mapped to points, incidence is preserved, and cross ratio is preserved. And oh, by the way, also, we also define a projectivity as a combination of such perspectivities. Okay, clear. So is it true that if we have these four things, then we can write it as a projectivity? Would that be true? Any ideas? Any guesses? Okay, so before I go on, what is an example of a map? Don't look at any of this first for a second. What is a map that keeps lines at lines, keeps points at points, preserves incidence, and preserves cross ratio? What is an example of a map that you guys know? Homotheity, yes, that's true. Anything else? I'll give another example. Rotations. Rotations also preserve this fact. Lines remains lines. Points remain points. If a point lies on a line, then this is true. And since all distances are preserved, this is obviously true. Everybody understands why a rotation would be an example of these things, right? Dilation, that's the same thing as homotheity. You do understand what I'm asking, right? I'm saying that if we have a map that preserves lines, that sends lines to lines, it sends points to points, it preserves incidence and also preserves cross ratio, then what's an example of such a map that you are familiar with? So like rotation satisfies all of these because the distances are the same. Points lie on points, lines lie on lines, and all. Any other examples? Well, that's not necessary to preserve cross ratio. I mean, I could define a map of points and lines that doesn't preserve cross ratio. Like I could just switch 2 points. Reflections, homotheity, exactly all of these. Translations, yep, translation also preserves cross ratio. Homotheity preserves cross ratio because all lengths are dilated by the same amount. Translations, all of these are true. But projective transforms include all of these and more. Okay. And so just because defining a rotation in terms of this is hard, I will actually just say it's a combination of perspectivities and affine transformations. Everybody know what an affine transformation is? No. Okay, so an affine transformation is all of these that you have mentioned. It's something that preserves linearity. So all of these are affine transformations because of the fact that the figure looks the same basically afterwards. Other examples of affine transformations are skew operations, in which you basically like you take a rectangle and you push the top part sideways and push the bottom part the other way. That's also an affine transformation. And okay, so I'll just skip over this for now. Okay. So now we're getting into one of the fundamental theorem of projective geometry in second dimensions, in 2 dimensions. And so, okay, so for what we do is, if we map any 4 points to any other 4 points, can we say that the whole plane will be invariant? can we define a projective map using only 4 points? That's the question. Like, how would we show that? Does everybody understand the problem? Basically, if T is a map such that T of A is A dash, etc., and T1 and T2 are two different maps, then is it true that T1 of X is always equal to T2 of X for all X? That's the question, basically. So anybody want to try this? I'll give you like 5 minutes. This is true if T1 and T2 are maps that preserve all 4 of these. So yeah, I'll give you 5 minutes, I guess. So the question is, if I have 2 different maps that satisfy these 4 things, they map lines to lines, points to points, they preserve incidence, and they preserve cross ratio for any 4 points lying on a given line. Then is it true that those 2 maps are identical if they are identical for 4 points? That is, do 4 points uniquely determine a projective map?
This is all in a plane, right?
This is, yeah, so this is one plane to another plane.
Oh, okay.
So this is one plane to another plane. T1 of X is equal to T2 of X. They are the same point. The cross ratio is AB. Cross ratio of AB, CD is AC by BC times BD by AD. I'll give you guys a hint. So you have to prove that if 2 different maps map these 4 points to the same 4 points, then they map every single point to the same point. So basically, I'll just explain it. If we take the intersection of AB and CD, this point, and so it must map to the image of this, because this line must map to this line. This line must map to this line by the incidence condition that lines map to lines. And so their intersection must map to each other, always. Does that make sense? Does that make sense? Why X would map to X dash? Yeah. Okay. And so now we know that this line maps to this line, and we know 3 points lying on that line. So therefore, every single point on this line must be uniquely defined. Does that make sense? So if I take like this point Y here, and suppose T1 maps it to some T1 of Y, and T2 maps it to some other T2 of Y, then since the cross ratio is the same for X, Y, AD, it must be the same for X dash T of Y, A dash D dash. So therefore, T1 and T2 of Y would be the same for every single point of on Y on this line. Does that make sense? Okay, and so basically this line is fixed. Each point on this line is fixed. Similarly, we can take this intersection, and so this line is fixed. This line is fixed. We can also take this intersection. So this line and this line is fixed, and then any line must intersect at least 2 of these, intersect at least 3 of these lines somewhere. So those 3 points will be fixed, and then the whole plane will be fixed. Does that make sense? Does anybody have any questions till now? Okay, so I've been pretty much just laying down axioms, talking about what projectivities are. Let me give you an actual question that you might have some fun. I mean, all of the previous questions were also actual questions. Given a quadrilateral ABCD, let BC and AD intersect at E. Let AB and CD intersect at F. Wait, actually, hold on. Actually, I can't give this to you right now. Okay, so before we go on, I will now. So we showed that we can map that any 4 points. If we map to 4 points, then the whole plane is uniquely determined. Now we can actually show that there exists a combination of perspectivities and affine transformations that can map any 4 points to any 4 points. And so I'm just going to go over this really fast because for the interest of time. And so here's a GeoGebra visualization. So what we do is we basically take the intersections of the sides, the corresponding sides, AD and BC, and take them to E. So if this is our quadrilateral, we take this intersection and this intersection. And so what we'll basically do is we'll send this line to infinity. Okay, so the second we send this line to infinity, what happens to these two lines? Parallel. Does everybody understand why they would become parallel? And similarly, these two lines would be parallel, right? Yeah. Okay. And so if these two lines are parallel, these two lines are parallel, what does that mean? What does that mean for ABCD? Parallelogram. Exactly. And so so remember I told you affine transformations include a screw transformation. Basically the basis vectors shift. So we can map this then to a square. Okay. I'm just going to skim over this part because affine transformations you guys don't know. And so basically then we take any 4 points to a square and then that square to any 4 other points. So we get a combination that we basically then take any ABCD to any A dash, B dash, C dash, D dash. Does that make sense? The outline of the proof. Anybody have any questions on what?
Are all affine, like all affine transformations cannot be defined as perspectivity combinations?
No, affine transformations preserve this fact that T of A plus B is T of A plus T of B. Which
But they also
basically
preserve the cross ratio and all those other facts, right? So
they
then-
do, but there are maps that preserve cross ratio, but they don't preserve this linearity because like I just showed you. I'm going to show you that when we send a quadrilateral to a parallelogram, there is no affine transformation that can send any quadrilateral to a parallelogram. It must send parallelograms to parallelograms because affine transformation preserve parallel lines.
My question was, are all affine transformations also projectivities?
Yes.
Oh, okay.
So why they're true, I won't get into, but you can actually convert them through various perspectivities. Okay. So and how we do that? So if you recall this map that we made, when we made a map of taking a plane to another plane, when we did this, all points were uniquely defined, except for a few. If we take the plane parallel to this plane, then those points on this line would never meet. Does that make sense? basically, if I take those points that lie, so this was our point O. This was our plane gamma 1. This is our plane gamma 2. If I take a plane parallel to gamma 2 going through O, this is parallel. And if I intersect this with gamma 1, if I take this line, then what would be the image of this line? That's my question. It would be a line, correct, but what line would it be? Because parallel things usually don't intersect. And this plane would then be parallel. So where would I intersect those parallel planes? Do you understand the loophole that's happening? So it's not lines that are parallel, it's the plane that is parallel entirely. So, okay, it will go to the line at infinity. And I'll show you how. So basically what I have, so now here what I have is I have 4 points A, B, C, D. I have EF. Okay. If I take a plane that's parallel to EF, if I take a plane that is parallel to this EF line going through P, then the image of E would not exist, because the image of E would be the intersection of this line PE with this other plane. Does that make sense? The image of point E would be PE intersection this other plane, but that wouldn't exist. Does that make sense? Or yeah, so that is a loophole in this construction. But if we consider the line at infinities, if we say that this point we're sending to the line at infinity, then that is not a loophole anymore. Does that make sense? So yeah, so in a similar way, F would also go to, so basically, so now to make a parallelogram, this is what we do. We take those intersections of those diagonal points, E and F. We take that line and we create a plane going through P, E, and F. Okay. The whole plane will not be mapped to infinity. The line EF will be mapped to the line at infinity. This line would go to the infinity line of this plane. And so using any plane that's parallel to that, if you look closely at those points, at the images of those points, you can actually see that they do form a parallelogram. Does everybody see how they are forming a parallelogram in this diagram? Right, like this point, this point, this point, this point, this point. They are forming a parallelogram because those lines will now approach to meet infinity. Okay. Okay. So now that we can send any 4 points to any other 4 points, we are actually ready for the question. So the question basically asks, given a quadrilateral A, B, C, and D, if we take BC intersection AD, E, AB intersection VC, F, BD intersection AC, G, we take FG and we meet these at P1, P2. We take EG, we meet these at Q1 and Q2. then prove that Q1 P1 and Q2 P2, their intersection is collinear with EF. Does the question make sense? So why don't you guys try it? I hope the question's clear. No, 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 not at all. There is no circle in this figure. I think you could use Pascal theorem by taking two sets of degenerate conics, parallel lines of whose theorem, two different one of those, and use that. I think that's possible, but there's a much simpler proof. Has everybody tried it? Should I go on to the solution, or do you want more time? No, so I haven't defined a cross ratio for non-collinear points. I'm not going to do that. And I know some authors do that, some people do that. I'm not going to do that because of the reason that when you take, so usually cross ratio, when you take any 4 points to any other 4 points, then if you define a cross ratio, that's automatically void once you take any 4 points to any other 4 points. Does that answer your question? Basically, like, if I define something like a cross ratio for any 4 points, then because I can send any 4 points to any other 4 points, like I just said, there would be no invariant. That would be useful. Does that answer your question, or? So I'll go on to the proof, since nobody's asking me to stop. Basically, we can send any 4 points to any other 4 points. So we send this to a square. Okay. And when we send this to a square, E becomes infinity, F becomes infinity, G becomes the center, P1, Q1 become this line parallel to the sides. P1, sorry, P1, P2, Q1, Q2. And so these lines are parallel. So they meet at infinity. And therefore, all 3 points are collinear at the line at infinity. Does that make sense? Does anybody have any problem with this solution? Okay, so basically I'm thinking of this as a square looking at it from a different angle. So in that case, point E becomes this point at infinity, corresponding to this direction. Okay. F then becomes this point at infinity, corresponding to this direction. Then P1, P2 becomes this line parallel to that direction vector, going through that center. Q1, Q2 becomes that line parallel to that direction vector going through the center. And since P1, P2, Q1, Q2 are now the midpoints, therefore these are parallel, and so therefore they obviously meet at infinity. It's basically looking at this figure, thinking of this. It's like thinking of this as a square and saying that, oh, it's obvious for a square, and we are just, this is a square, but we're just looking at it from a different angle. Yes, all three are parallel. That's why they meet. That's because we know that these 3 points meet at F. So now these 3 points meet a point at infinity. So obviously it seems a bit like magic, like we took 4 points to a square. And that's why we need a lot of that terminology, that boring part that we did earlier, how we take 4 points to any 4 points. But in truth, it's, yes, lines weren't meeting. So that's why we need a lot of that groundwork, because see, lots of things in math, you will come around proofs that are 1-line proofs or 2-line proofs, and you're going to look at them and say, wow, that's amazing. But there is a lot of stuff behind, principles behind that you should know before using such proofs. And so the fact that we can send any 4 points was used in this. Okay, so any 4 points to any 4 points, that's really good. But remember, we can only talk about intersections, right? We can't talk about circles and all that. So because you will soon see that when we take a projection, that circle could no longer be a circle, because as someone just said earlier, when we take another plane cutting a cone, that could be a hyperbola, that could be an ellipse, that could be 2 lines, it could be a parabola, it could be anything, right? And so that's why circles don't map to circles. Does that make sense? Why circles don't map to circles? If anybody's done any bit of drawing, then you'll see that glasses are made like this and cylinders. This is an ellipse, but we treat it as a circle, right? So that's kind of the thing, that you can't use circles that well in projective maps. But there is one type of projective map that you can keep a circle, right? You can have your cake and eat it too. And so the way that works, it's called a stereographic projection. And so wait a second. And so what a stereographic projection does is it takes a sphere it takes a point, it takes a pole of that, and it sets any point on the sphere to a plane. Okay. So obviously this goes into hyperbolic geometry and all of that, and I don't want to get into that. But the thing is that for any circles, this maps circles to circles. Okay. And just as an example, here I do have a stereographic projection set up. And so basically, as you can see, I have taken a point on the circle. I have intersected TC. Wait a second. Yeah, now it's working. So basically, I took a circle, I intersected it, and then any point on that would map to a circle. So that's like how we're mapping a point. And so this preserves circles. It's pretty useful. Does anybody know how we would prove this? I'll give a hint. It uses coordinate geometry. Okay, so I guess I'll just explain it. So basically, we set up our coordinates as this point is 0, 0, 0. Let's actually flip this way. So now our x-axis is here, y-axis is here, and z-axis is here. So this sphere becomes x minus 1 square plus y square plus z square is equal to 1. The intersection of this circle would just be a plane ax plus by plus cz is equal to d. Where a, b, c, d are some constants that would define that circle. And then that intersection we want, so for any point x, y, z that lies on the circle, the stereographic projection of that would be x by z, y by z, 1. Because whenever we map a line, whenever we take a line through an origin, it basically takes a, b, c to some lambda a, lambda b, lambda c, and we want z is equal to 1. Z is equal to 2 in this case, actually, so something like this. And then we can use this, homogenize this, and you get the equation of the circle. Okay, does everybody understand that proof, basically how it's going? Anybody? Okay, I guess I'll not stress too much on this. You can do it on your free time. It's not that hard. And so basically now what we can do with this with this stereographic projection is that one thing to note is that it doesn't map centers to centers, right? In fact, it will map a different point to the center. In fact, if we take a plane like this, cutting it in half, this becomes a circle. And this diameter goes to this diameter. So the centers are not necessarily collinear. And in fact, if they were collinear, then that would imply this parallel to this. And so basically how we use this is that by suitably choosing these points P and Q, what we map this center to is to some other point X, and that X could be anywhere in our circle. So now, so basically we use this in reverse. Like if we have a point X in the circle, what we do is we set up as this as the diameter. Like if this was X, this A, this B, we think of the circle as this. And so then when we take the stereographic projection, X then becomes the center of the circle. Does that make sense? Okay, so I'll just take it for granted that you can send a point inside the circle to the center. And we're just going to use that to prove one of my favorite theorems in geometry. It is the butterfly theorem. Does everybody know what the butterfly theorem is? Okay. Does anybody know a proof of the butterfly theorem? No? I'll just go over my favorite proof before we get into the projective one. We basically take reflection of C over M, B over A. Then this turns out to be cyclic using power of a point. And then you consider and then you find that this also becomes cyclic. And so you use use the three radicals intersect on these three circles to find that these are collinear, and then this becomes the map of this. Okay, never mind that. I'll just go into the projective proof. So in the projective proof, what we do is, what would be a good choice to send M to? Where should we send M if we want to look at this in a different way? Yes, the drawing perpendiculars proof, I think it's given with coxeter. It's very bashy. This one's a bit more synthetic. That's why I like it. Okay, so we're going to send it to the center. The instant we send it to the center, what happens to all these chords? Exactly, they become diameters. So XY is a diameter, AB is a diameter, CD is a diameter. Now, remember, we don't actually have a condition for the midpoint. Remember that, right? We can actually map any 3 points to any 3 points. So we don't have a condition for midpoint. But what we can say is that if there is a corresponding infinity point to this, then the cross ratio of this is -1. Does everybody understand why this would be -1? Okay, so this will be -1 because xm by my is 1 and xp infinity by yp infinity is -1, basically because these two lengths are the limit as p towards infinity, those tend to 1. Those become almost equal. Okay. Okay, so basically now the theorem states to prove that if we look at this at a different angle, then we want to show that this length is this length. Does that make sense? Does anybody have any question up till now? Okay, so basically, I'm going to skip over this fact as well, because I think it will require a lot more stuff. Okay, so I'll just go to one last example, and after that, I think time will be up. So, does anybody know about this statement? If you take a fixed point O inside a circle, take any two chords going through it, then the intersection, I'm going to take a better diagram. Then the intersection of the two opposite points, the locus of that will always be a line. Does anybody know this? Anybody heard of this problem? Yes, no. So basically it says that we have a point fixed inside a circle C. We take any two chords, AB and CD. We intersect AD and CV at E. Now we take the locus of E as AB and CD both vary. Then that locus is a fixed line. Which is actually quite amazing because you have 2 degrees of freedoms here and you only have 1 degree of freedom here. So it's kind of interesting. Okay, so this is actually the definition of poles and polars. For those who know what poles and polars are, this is one of the definitions. It's a purely projective definition of pole polar because it uses no concept of inversion, no concept of perpendicular. And the reason why it's true is that if you take O to the center, then AB and CD, they both become diameters. And basically at that instant, this whole thing becomes a rectangle. So E then must be a point at infinity, and therefore it must lie on a line on infinity. Right? And so basically whatever AB and CD you take, E will always lie on a fixed line that is the line at infinity. So when you go backwards, the pre-image of the line at infinity, E would always lie on that. Does that make sense? Every point has an image. Every image has a pre-image. That is by definition a bijective map. Okay, so I guess I'll just wrap it up now because of poor attendance and everybody's sleepy, I guess. So and also we're at 8:30. So before I leave, any questions related to math in general, or Olympiads, or applying to colleges, anything of that sort?
Should I like end recording before that?
Yeah, sure. End the recording.